Hello everyone. We are Group 12 from the Data Analysis for Research course. I am Divyasri and along with my teammate Surendran R, we are here to take you on a journey into the world of statistics. Every strong system is built on solid pillars and today we'll explore the very first one, the foundation stone called aggregation. Let's dive in. This course, we are learning about the building blocks of data analysis and in that journey, aggregation stands as the first pillar, the foundation on which modern statistics and data science are built. In this presentation, we'll explore how aggregation emerged, why it matters, how it has been used throughout history, and why it remains central to research today. So, what is aggregation? Aggregation simply means combining many observations into a summary. Instead of focusing on every single detail, we bring them together to see the overall pattern. For example, the mean or average is a simple form of aggregation. Now, why does this matter? Why aggregation matters? Averages and summaries may hide some details, but they help us recognize general trends. Different observers and tools may give different results, but when we combine them, we often get a much clearer picture. To understand this idea more deeply, let's look at how people began using aggregation long ago. The main power of aggregation lies in reducing noise. When we combine multiple data points, errors cancel out and the true pattern emerges. This principle has guided statistical thinking for centuries. Now, let's go back to the roots of aggregation. Even in ancient civilizations, people aggregated data. Sumerians, for instance, used crop tables as early as 3000 BC. They would add rows and columns to summarize events. This simple tabular thinking later became the foundation of modern statistics. Let's see how these ideas were used in society. Historical uses. Aggregation shaped practical life. For example, siege ladders were built using the most common soldier height, essentially the mode. Communities averaged men's feet to define a standard foot measure. These everyday examples remind us that aggregation has always been a way of creating order from diversity. With time, these methods became more refined. From simple averages to smart methods. At first, people relied on the mean, but as science grew, new tools were needed. Eventually, least squares emerged as a method to minimize errors when combining measurements. Before explaining that, let's understand why aggregation is mathematically powerful through the law of large numbers. Strength in numbers, the law of large numbers. The law of large numbers tells us that with more observation, averages become closer to the truth. Random variation cancel out. This principle is why larger samples are trusted in surveys and experiments. A brilliant demonstration of this can be seen in astronomy. In 1874, scientists around the globe observed the transit of Venus. Different instruments, different conditions, different results. But when combined, these measurements helped refine our knowledge of the Earth's sun distance. However, the aggregation also has risks. The risk of averaging. Averaging sometimes hides important differences. There is also a temptation to select only the best looking data, which can lead to a biased result. The problem has been debated in economics too. Economist William Stanley Jevon argued that averaging prices reveal economic trends. Critics countered that combining unlike items such as food and metals could distort reality. For instance, a spike in pepper prices might be hidden in a stable index. Similarly, in other sciences, aggregation can both clarify and mislead. The average man. Catlett introduced the concept of the average man using the population averages. While this helped understand population statistically, critics pointed out that the average man may not represent any real person. This is a reminder that aggregation is an abstraction. Galton combined multiple faces into composite images to show an average face. While this reveals some patterns, it also created unrealistic faces if unrelated groups were combined. This was a caution against careless aggregation. Literature too has reflected on this. In Berg's story, Funes remembered every detail but could not understand general ideas. Berg wrote, "To think is to forget a difference, to generalize." This beautifully illustrates why aggregation is essential. It allows us to move from endless detail to meaningful understanding. In science, this became critical in debates about the Earth's shape. In the 1700s, scientists debated whether the Earth was oblate or prolate. Measurements of latitude gave conflicting results. To resolve this, aggregation methods were used to combine observation and reveal the true shape. This led directly to more advanced mathematical tools. Boscovich developed an approach to minimize total error across conflicting measurements. Later, Legendre formalized this as the method of least square. This was a milestone in the history of statistics and is still widely used today. But aggregation is not just historical, it powers our modern world. Today, aggregation is everywhere. In science, it's used to combine experiments. In economics, to build indices. In social sciences, to analyze populations. In technology, it underlies machine learning and big data analytics. But why do we rely so much on aggregation? Why we aggregate data? We aggregate to simplify complexity, to see hidden patterns, and to create standard measures for decision. In short, aggregation makes data usable, but more than purpose, it also offers key benefits. The benefits are clear. It reduces random errors, reveals overall trends, and makes huge amount of data manageable. Without aggregation, we would drown in details without understanding. Let's look at some concrete illustrations. Aggregation power weather forecasting by combining models. Opinion polls average responses to predict election. Scientific collaborations pool results across labs. These examples show how aggregation transforms uncertainty into insight. Now let's bring it all together. Aggregation transforms details into understanding. It balances detail with generalization and it has guided human thinking from ancient table to modern algorithm. Let's close with the main lesson. First, aggregation is not new. It has deep historical roots. Second, it makes pattern visible but can also hide details. And third, it is the foundation of modern data science. In short, aggregation is the art of turning complexity into clarity. As we come to the conclusion of our presentation, let us reflect on what we have learned. From the earliest crop tables of the Sumerians to the development of least squares and in modern sciences, aggregation has always been a way for humans to make sense of complexity. It is through aggregation that we are able to transform scattered observation into meaningful knowledge. We saw how aggregation helps us simplify large and messy datasets, reduce random errors and highlight true patterns, provide common standards that societies and sciences can rely on, and serve as the foundation for decision making in economics, science, and technology. But we also acknowledge that aggregation is not without risk. While it reveals general truth, it may also hide important differences or even mislead when applied carelessly. This balance between detail and generalization is at the heart of statistical thinking. That is why we describe aggregation as the first pillar of data analysis. It is not just a mathematical tool, but a guiding principle that allows us to move from confusion to clarity, from detail to understanding, and from raw data to knowledge. In today's world of big data, artificial intelligence, and research driven decision making, aggregation remains as essential as it was thousands of years ago, perhaps even more so. With this, we conclude our presentation. Thank you for your attention, and I hope this journey through the history and purpose of aggregation has shown both its power and pitfalls.